Hello, I am Samar Haddo, and this is a short talk about our paper, Space-Time GNNs with Stochastic Graph Perturbations, a collaboration with Jair Solis and Alejandro Ribeiro. We have encountered data supported on graphs in applications like social media and knowledge graphs, among many others. And GNNs have been developed to learn representations from these data, where both graphs and node attributes are usually considered fixed or slowly changing over time. However, these assumptions don't fit some applications like multi-agent systems, where the agents move very rapidly and their positions are considered the node attributes. And that comes with two challenges. First, the graph connecting the agents changes over time, and we might start with the graph on the left, and in the next time step, the agents move to new positions, forming a new graph like the one on the right. And the question is, which graph to choose in learning? Second, data aggregations is susceptible to time delays. That is, when an agent transmits its data, this data will only be available to their neighbors in the next time step. But by that time, every agent will have already acquired new data, which means that the nodes make their predictions based on outdated information. And the question now is whether we still can learn representations under these challenges and whether we can generalize these learned representations to unseen examples. And the answer to both questions is yes, we can, thanks to space-time GNNs. In today's talk, we aim to show that space-time GNNs indeed can handle these challenges and they are stable to stochastic graph perturbations. But first, let me give you a quick recap of space-time GNNs. Well, they are convolutional networks where the convolution block is a composition of both time and the graph convolutions. And as we recall from classical signal processing, time convolution is defined as a weighted sum of time-shifted versions of signal x, which we can write in a matrix notation using a circulant matrix C, since multiplying x by c shifts the signal by one step. And when we raise c to the power k, we shift the signal k time steps. And by analogy, graph convolution just replaced C with a graph shift operator S that can be chosen as the graph adjacency or Laplacian. Another way to think of it is that this shift operator S aggregates information from the direct neighbors, and when we raise it to the power k, the agents receive information from their k-hop neighbors. And combining the two produces space-time convolutions, in which information received from a k-hop neighbor has been delayed k time steps in time. This ensures that the GNN won't see any present data from the neighbors during training and will learn to make predictions from outdated information, which checks the second box of our requirements. And now, space-time GNNs are just a cascade of these convolutional filters followed by nonlinearities. And note that they are both permutation and translation equivariant. But this form relies on just one shift operator S that represents one fixed time graph. But we promise to find a solution for dynamic graphs. So how to go from a case with a fixed time graph to a case where graphs are dynamics? Our approach in this paper is to train a GNN with a fixed graph and then transfer this learned network to cases with dynamic graphs. We know that this is only possible if we can bound the distance between the output of standard space-time GNN on the left with the one with the dynamic graphs on the right. That is, we show that small change in the graphs yields small change in the outputs, and therefore transfer learning is possible. But to bound this difference, we first need to define this quantity on the right, which brings us to our proposed generalized space-time GNNs. And let's go back to the equation of shifted signals. As we know by now, the shift operators right next to x are responsible for shifting direct neighbors' information by a one-time step. But by the time we apply them for a second time, we know that the graph has changed and S became S2. And by the time we aggregate information from the k-hop neighbors, we would have encountered k different graphs. Therefore, we can replace S to the power k with k different S's representing k different graphs, which let us write this generalized form for space-time convolutional filters. And just like before, we can define a generalized space-time GNNs that accommodate dynamic graphs as well as time delays. But is it efficient to train this model? Well, training in this case would require storing different graphs for each example in the dataset. And if we have large size graphs and large datasets, that might be overwhelming. That gives us a good reason to prefer transfer learning from fixed time graphs. But this is only would be possible if we shows that space-time GNNs are stable to stochastic perturbation. But why is this a specific type of perturbations? Well, we definitely don't think that this is going to hold for any graphs. So we restrict our attention to the case where the edges of each graph in the dynamic sequence are sampled from a fixed time graph with a probability P. This is a common practice in multi-agent system where we assume that the links between the agents have a drop probability 1 minus P. And this makes each graph STK appear like a perturbed version of the original graph S. And the larger the drop probability, the larger the distance between the two graphs. And now, by expressing dynamic graphs as stochastic perturbations of a fixed time graph and under smoothness assumptions of the space-time filters and the nonlinearities, we were able to prove that, on average, the distance between the output of the trained network with a fixed time graph and with dynamic sequence of graph is bounded by a factor that is linear in the drop probability 1 minus P up to some constant. And this constant depends on the graph size n, the number of layers L, and some Lipschitz constant CL and C sigma. This indeed implies that we can transfer learning to dynamic graphs if the drop probability was kept small. And to verify our theorem, we consider the application of following a moving target, where we train a space-time GNN to follow a target using some noisy measurements of its trajectory and velocity. And the dataset consists of agent trajectories and their communication networks as inputs, along with their accelerations as outputs. And we were able to learn policies for different numbers of agents as shown in this figure, where the right column shows the agent velocities at the beginning of the simulations and the left column shows them at the end. And to demonstrate the stability bound, we ran additional experiments where we constructed the underlying graphs by sampling from a fixed time graph with probability P. The results show that the bound is indeed linear with the drop probability, and we ran these experiments for both space-time GNNs with nonlinearities and the filters without nonlinearities. And the linear bound holds for both, proving that transfer learning is indeed possible. And by that, we reach the end of our presentation. Thank you for watching, and we are looking forward to see you in ICASSP.